Okay, thank you. So today I'm going to be talking about moment maps in complex geometry. And I guess the general theme is important or canonical equations in geometry. So what are some examples? Well, there's the CSVK equation, Hermite Einstein equation, the J equation, and also many others. But what unites all of these examples is that they're all examples of moment map equations. So these are all moment maps on infinite dimensional spaces. And what I want to discuss in this talk is a new way or a new approach to generating such moment map equations, getting our hands on them. The idea is to take some topological data as input and produce a geometric equation as the output. And this is going to be a PDE as the output. So that's what the approach does, and what the approach uses as a central idea is equivariant cohomology. So the main tool, I guess not even equivariant cohomology, just equivariant differential forms. So equivariant differential forms. So what I'll start by doing today is just giving a quick review of equivariant cohomology. Equivariant forms in cohomology. So in this section, we'll let K be a compact Lie group with Lie algebra curly K, frac K. And we want this to act on a smooth manifold M. And in this situation, we define an equivariant differential form to be the following. It's a K equivariant map, polynomial map, from the Lie algebra K to the space of differential forms on M. There's an appropriate notion of degree for such equivariant differential forms, which I won't go into in too much detail, but basically for the differential form part, the degree is as usual. And for the polynomial part, say you have some homogeneous polynomial of degree k, that gets given degree 2k as an equivariant differential form. So a linear map from here to here, which is k equivariant, the linear part would give you degree 2. On equivariant differential forms, we have an equivariant exterior derivative. So yeah, let me say I have an equivariant differential form alpha. I would define dx of alpha. Well, that needs to be a map from the Lie algebra to forms, so I need to evaluate it on an element of the Lie algebra. And what I do is I just take the usual exterior derivative of alpha v plus the contraction of alpha v with the vector field generated by v. So this is vector fields on M. And this is for all v in the Lie algebra. So I have equivariant differential forms, and on those I have an equivariant exterior derivative. So this satisfies dx squared is equal to 0. So we get equivariant cohomology. Defined as follows. So it's just the kernel of dx modulo the image of dx. And this is equivariantly closed forms over equivariantly exact forms. The cohomology groups themselves won't be so important in this talk. What I'm really interested in is just the equivariantly closed forms, essentially. So those are all the abstract definitions, but let's give an example. So I want to let omega be a closed two-form. On M. And mu, I want to be a k equivariant map from M to the dual of the Lie algebra. And these things on their own are already equivariant differential forms. I can add them together to get a new equivariant differential form, omega plus mu. And then omega plus mu so this is, well, i.e. the form V maps to omega plus the pairing of mu with B. Is equivariantly closed if and only if the following holds. So the contraction of omega with any vector field generated by the Lie algebra is minus d of the pairing of mu with that element of the Lie algebra. So this is for all B and K. And probably this is a familiar property. This is the moment map equation. So really we can think of equivariant closed two forms as moment maps. So in some sense equal, in quotes, moment maps. So just a note on my terminology, usually when you talk about moment maps, you require the two form to be symplectic. In this talk, I'm not going to require that. So I'm just going to be considering arbitrary two forms, and I'll still call this equation a moment map equation, even if the form isn't necessarily symplectic. So yeah, it's a bit of an abuse of terminology. So that's an equivariantly closed because so you have a polynomial map. This is mu is a degree 1 polynomial, but degree 1 as a polynomial means degree 2 in the equivariant cohomology ring. Yeah. So that's basically just how you define the degree in equivariant cohomology. Essentially, yeah. So yes, this is an equivariantly closed two form. I want to generate more examples. And I'll do this using a couple of facts. So fact one, if alpha and beta are equivariant, and I'll say closed / exact, but they don't have to be, forms, so is alpha wedge beta, which we define by just taking alpha v wedge beta v, for all v in the Lie algebra. So we can wedge equivariant differential forms. If the two forms we're wedging are closed, then we get a closed equivariant form. If we wedge a closed form with an exact form, we get an exact equivariant form, and so on. And yes, in terms of degrees, the degree of alpha wedge beta is deg alpha plus deg beta. Fact two, so say we have a proper submersion. So M over B is a proper submersion. Oh, and I want K equivariant. So in other words, I have a K action on M, a K action on B, and the projection map is K equivariant. And alpha is, again, equivariantly closed or exact on M. Then we can integrate alpha over the fibres. So, and so is integral x over b alpha, which we define by integrating alpha of b. And again, this changes the degree. So the degree of this fiber integral is just the degree of alpha minus the degree of the, the dimension of a fiber. Right, as m little b. Okay. Yes, yeah, I've got a proper submersion. Yeah, so I can integrate. Yeah. Oh, that's m. Yeah, sorry. So yeah, this is pretty good. So if I have a couple of equivariantly closed two forms, I can wedge lots of copies of them to get more equivariantly closed forms. And if I have a submersion, I can integrate such a form over the fibers to get a new equivariantly closed form. So that will allow us to discuss most of the examples that will be in this talk. I'll just need one more slight generalization of equivariant forms. So generalization let's let E over M be a complex vector bundle. And I want K equivariant. So I have an action on M by K, which lifts to the vector bundle. A K invariant connection on E with curvature FA. Then I define a moment map for the curvature. Is to be a K invariant section. So right is mu A. And it should be a section of the dual of the Lie algebra tensor endomorphisms of E. So for each element of the Lie algebra, I get an endomorphism of this vector bundle. Such that the following holds. So the contraction of FA with any vector field generated by the Lie algebra is minus the connection applied to mu A paired with V. Roll V in the Lie algebra. So it's just the same as the moment map equation, except instead of usual differential forms, I now have differential forms with values in the endomorphisms of E. So this is an equation in ND-valued one forms. And I replace the exterior derivative with the connection that I'm working with. And I won't give an example of such a generalized moment map just yet, but we'll see one later in the talk. Why do I want this? Well, this lets us find representatives of equivariant characteristic classes of E. So for example, we can write down a representative of the kth equivariant Schoen character. And whenever I use a representative, I write this tilde notation to mean that I'm taking representative. So this is 1 on k factorial, trace of I on 2 pi. Yeah, I need an extra bracket here. Curvature A plus mu A all to the k. So when we have an equivariant vector bundle, we can construct K-equivariant moment maps and use those to find equivariant differential forms. So yeah, the curvature is what we would call like an endomorphism valued equivariant form. But down here, once we take the trace, we lose the endomorphism part and we just get a genuine equivariant differential form on the manifold. So those are all the examples. Are there any questions before I move on? Yes. Yeah, it should be. Yes, yes, it would be. Yeah, because the endomorphisms are just functions, right? Yeah, of course. Yeah. Okay. So that's all the background. I now want to give an example of how we can use all this equivariant machinery to construct an example of a moment map equation. And the equation that I'll pick is the CFCK equation. So let's suppose that K acts on M omega M, a compact scalar manifold. And we'll assume that the action has a moment map mu M. Then we have equivariantly closed two forms. On M. The first one is just the definition of a moment map. So I assumed omega, or sorry, mu M was a moment map for omega M. So that's automatically giving us an equivariant form. The other one is a result, the Ricci curvature of omega M minus the Laplacian of mu M. This is also an equivariant or equivariantly closed two form on the manifold M. That's something that needs proving, but I'm not going to prove it. I will use it though, and we need also a relative version. So yeah, here I'm just fixing a manifold M, but really what I want is a fibration so that I can do this integration over the fibres that I mentioned. So let's let X over B be a proper holomorphic submersion. K equivariant. Keep forgetting to write that. So I have an action on the total space and the base, and the projection map preserves that action. And I'll let omega be K invariant, relatively scalar metric on X. So omega is a real closed 1-1 form on the total space X, and its restriction to any fiber is a scalar metric. So I have positivity in the vertical directions, but I don't require any positivity in the horizontal directions. And I'll say with moment map mu. So here's the first instance in which I'm abusing terminology. Omega doesn't have to be a symplectic form, but I'm still calling mu a moment map for omega. Then omega induces a metric on the top exterior power of the vertical tangent bundle, which you can think of as minus kx over b. If you're more into algebraic geometry. So yeah, the dimension of my fibers I'm taking to be little n. And this metric has curvature. So with curvature, rho in the first term class of that line bundle. So rho you can think of as like a relative Ricci curvature. So if I restrict rho to any fiber, then I just get the Ricci curvature of omega restricted to that fiber. And in this setup, we have equivariantly closed forms. First is omega plus mu. And the next is going to be rho minus, instead of Laplacian, I only have a Laplacian in the vertical directions. So rho minus the vertical Laplacian of mu. So Laplacian V equals Laplacian on fibers. Okay. So now, this is everything I need to generate a moment map on the base of my fibration. So how do I do that? I want to integrate some equivariant forms over the fibers. I need them to have the correct degree so that I get a 2 form on the base. So first example, so we produce equivariant closed 2 forms on B by integrating equivariant closed 2n plus 2 forms over fibers. So I just need to choose some 2n plus 2 forms, integrate them, and I get equivariantly closed 2 forms on the base. So the first one I'll pick is the following. So I'll integrate x over b rho minus vertical Laplacian of mu, wedge omega plus mu to the n. So I'm just taking a combination of these 2 equivariantly closed 2 forms that I wrote down and integrating over the fibers. The result of this will have a 2 form part and a function part. So the 2 form part is rho wedge omega to the n. And then the rest will just be function parts. So next I get integral x over b n times the moment map rho wedge omega to the n take 1. And I also get an integral of this, so minus x over b vertical Laplacian of mu omega to the n. So This vertical Laplacian is just the fiber-wise Laplacian. I'm integrating over the fibers. When I integrate the Laplacian of the function, I get 0. So this last term vanishes. The two-form part stays the same, but I can rewrite this function part here as the integral of x over b with mu against the scalar curvature of a fiber. So little b, I'm thinking of a base point in the base b, and s omega b is just the scalar curvature of the fiber at that point. So I'm integrating scalar curvature against the moment map. That was the first form I wanted to integrate. The other form I'll integrate is the following. So omega plus mu to the n plus 1. This is very easy. I just get, as my two form, integral over the fibers of omega to the n plus 1. And as my function part, integral of mu against omega to the n. So, okay, I've now got two equivariantly closed two forms on the base of my fibration. I just want to finish by taking a linear combination of those. So combining, I'll take the average scalar curvature of a fiber divided by n plus 1 times the second form I wrote down, minus the first form that I wrote down. The equivariant forms. And when I do that, what do I end up with? So I get a two-form part, which is as follows. So it's average scalar curvature of a fiber divided by n plus 1, integral x over b omega to the n plus 1, minus this other term, rho wedge omega to the n. And as my function parts, I get the following. So I get the integral of the average scalar curvature of a fiber minus the actual scalar curvature of a fiber against the moment map mu omega to the n. Sorry? Yeah, it doesn't appear in the final equivariant form, just vanishes. So what have we done? We've produced an equivariantly closed two form on the base of our fibration, but the function part is the integral of the scalar curvature against the moment map. So what we've proven, in a sense, is that the scalar curvature is, integral of the scalar curvature against this moment map. So we've proven that this integral is a moment map itself. Just kind of magic. All we did was write down some equivariant forms and integrate them, and we produced a moment map equation. So observations. Exactly, yes. Yeah. So first observation, this gives us the moment map and the two forms at the same time. And if you're familiar with Donaldson-Fujiki picture, this might look familiar. This is the Peterson metric. Maybe I shouldn't use the word metric because the next comment is that we actually get no information about positivity of the two form. So we don't actually know the two form is positive, i.e. symplectic. All we get is some two form plus a function, which is a moment map for that two form. But we don't know that two form is scalar or positive. What other information can we glean from this? Well, notice that if we take take B equal to P1 and integrate the two forms, we get the Donaldson-Futaki invariant. So we get, or at least the formula for the Donaldson-Futaki invariant. Obviously, this gives us nothing about test configurations or singularities, but at the very least, we can observe what the formula for stability should be from this moment map. And finally, the last comment I want to make is that this works. So I've been working in the finite dimensional setting, but this works in both finite and infinite dimensions. Okay, what do I mean by infinite dimensions? I mean the base being infinite dimensional, because I still need to integrate over the fibers, so I need compact finite dimensional fibers. Exactly, yes. Yeah, so that's one example you can recover using this, is the Donaldson-Fujiki moment map picture. So if you take your base to be that space of almost complex structures. Yes, yeah.
I mean, the remaining part looks like the product, right? So what do you mean by integrating on P1? So you're integrating just the part in the bracket of P1.
Yes, yes, exactly. So when I take B equal to P1, this is a two form on P1. So when I integrate that over P1, it's the formula for the Donaldson-Futaki invariant. So yeah, if I genuinely did have a smooth test configuration, then that would be the Donaldson-Futaki invariant of that smooth test configuration. Exactly, yeah. Okay, so that was an already well-known example. What I want to finish by doing is showing how we can get a new example of a moment map. So for new examples, and at the beginning of the talk, I mentioned we kind of what I want to do is associate to topological data a moment map equation, and it's maybe not so clear how that happened in this setting. But what I'll do in this section is maybe describe that a little more clearly. So for the CSCK equation, we had topological data on the fibers of our fibration, which was Ricci curvature, wedge, the metric to the n-1, And this is the kind of topological data that generates the scalar curvature equation. What I want to do in this section, so we'll now associate a PDE to the data, where instead of just, well, this is really C1 of a fiber. Now I instead want to take a churn character of a fiber. So I'll look at the kth churn character of a fiber wedged with omega b to the j. So here j plus k is equal to n, is the dimension of a fiber. So I'm choosing this as my topological data on the fibers, and I'm going to show you how we can generate a geometric equation just from that data. And before I need to do that, I now need to give an equivariant representative of the churn character. So let's go back to the non-relative setting. So let K act on our manifold M omega M. And I want Rm to be the full curvature tensor of M omega. I can write down a moment map for this full curvature tensor. So a moment map for RV is the following. Sorry, Rm. I'll write H, which will be an endomorphism of the tangent bundle. And I want it to be G inverse of I del del bar mu m, where mu m is a moment map of omega m. So yeah, this is an endomorphism in Tm 10. I'll explain this notation in a second. So I del del bar of mu m what is this? It's a 1-1 form. So it's a section of T star M 10 tensor T star M 01. But by the metric, I have an isomorphism between the 0-1 forms and the 1-0 vector fields. And that's what I mean by G inverse. So by G inverse, this is isomorphic to T star M10 tensor TM10. And this is, of course, is endomorphisms of TM10. And okay, this is actually a generalization of a moment map we've already seen. So yes, yeah, sorry, yes. Yeah, tensor K star. Thank you. Running out of chalk. Okay. So if we take the trace of this end Tm valued form, we get exactly what we had before. We get rich omega m plus Laplacian of mu_m. So you can think of this as a vector undervalued generalization of the fact that this is an equivariant form. But what we can do with this is we can get equivariant representatives of Chern characters. So an equivariant representative of K Chern character of M is just 1 on K factorial trace of I on 2 pi Rm plus H all to the K. But once again, it's not that simple. Now I need a relative version of this. So just like before, how I had the relative Ricci curvature and I had the fiber-wise Laplacian, I just want a generalization of this equation to the relative setting. Oh, where did that go? Oh. So let's, again, X over V be a holomorphic K equivariant submersion. I want V to be the kernel of the projection. That's my vertical tangent bundle. And I'll let R curly V be the curvature of this bundle Z with the restriction of omega to that. So omega defines a Hermitian metric on the vertical tangent bundle. And then I get a moment map for RV, which is the following. I write it as HV, which is, okay, now I just want the vertical metric, and I want to take vertical derivatives and use my moment map. And this is now an endomorphism of V10. Yeah, so this is what I was talking about in the beginning of the talk. So I had an example of vector bundle valued moment maps where if you have a K equivariant vector bundle and you take its curvature, then it's the same moment map equation except you use the connection instead of exterior derivative. So yeah, maybe I'll write down explicitly what this means. Yeah, I guess I'll do that here. So in the non-relative case, it just means that you get minus the Chern connection applied to H, the endomorphism. And in this case, I get pairing with V. Yep. And in this case, I get minus the Chern connection of curly V applied to HV. Right. So an equivariant representative for the K Chern character of V, or equivariant, is the following. So CH KX tilde V omega usual thing. Okay, so now I've got my equivariant form and I can generate examples using this topological data that I wrote down earlier. So let's do that. So step one. I want to take this topological data that I wrote down and I want to do the following. So there's a power of omega. I want to divide by that power plus 1. And I want to take the kth character of the vertical bundle and increase the power of omega by 1. And I've removed B because I'm no longer thinking of this as a class on fibers, but as a class on the total space of the fibration. So that's the first step, is just modifying this topological data. Step 2 is we take an equivariant representative which is the following. So, oh, I already wrote it down up here. So EHKX tilde the omega wedge omega plus mu to the j plus 1. Step 3, okay, so now we've got, this is a 2n plus 2 form on the total space of our fibration. We just need to integrate it over the fibers. So step 3 is to take fiber integral of x over b, ch tilde x, the omega wedge omega plus mu to the j plus 1. And we get a two-form part as usual, which is the non-equivariant representative, wedge omega to the j plus 1. Sorry, I wanted to divide by j plus 1. And we also get function part. So first we get the expansion of this. So we get mu integrated against chk tilde, the omega, which omega to the j. And then we get the more complicated term, which is what happens when we expand the power of k in this Chern character, and we pick up one copy of h. So what happens there? So we get 1 over k minus 1 factorial now. Still have the 1 over j plus 1. Trace of I on 2 pi still to the k. Rv to the k minus 1 hb, which omega to the j plus 1. Now, to produce our moment map equation, we want to be integrating against mu. And whatever is being integrated against mu will be our moment map equation. But the problem is, in this last term here, mu is hidden in here. So remember, this term is GV inverse, I del V bar, mu. So step 4 is to somehow extract mu from here. And I don't have time to do the calculation in full, but what that involves is integrating by parts, basically. Yes, now we have to deal with it, so it becomes a problem. Yeah, you need to genuinely integrate by parts and figure out what to do with this term. So step 4, is integration by parts. And what you get is a function part as follows. So variable x over b mu against the following big ugly thing, 1 over k factorial I on 2 pi rv to the k, which omega to the j divided by omega to the n plus 1 on j plus 1, a bunch of constants, I on 2 pi to the k, 1 on k take 1 factorial, I del bar star del star r curly v to the k minus 1, which omega to the j plus 1 over omega to the n, and I'll include a notation flat there, all against omega to the n. Yes, so this down here, this big ugly thing in the brackets, is the moment map equation that we get. And yes, I'll just finish by saying that we can get more general things. This was just one example of a piece of topological data, but we can take general linear combinations, complex linear combinations, and we end up with what we call Z-critical calorimetrics. So yeah, I should say that setting this equal to a constant is our moment map equation. All right, that's all. Thank you.
Linear combination.
Yes. You can wedge the Chern characters. Yes, exactly. And that gives you kind of the most general topological data you can write down. Because the Chern characters generate all of the characteristic classes, so it's sufficient to do this calculation just for Chern characters, and you can get any topological data you like. Yes, yeah. Yeah.
The corresponding Putaki variants are the Pandu Putaki variants. That's correct.
Which?
What is the PD that you get out of this formula?
It's setting this thing here in the brackets equal to a constant. That's the PDE. Yeah.
That thing, Chern form is harmonic.
I don't think so. Yeah, it seems a lot more complicated. I mean, this is like an order 6 differential equation in the Kähler potential because for the curvature, you take 4 derivatives of the Kähler potential, and then you're taking another 2 derivatives.
Right.
So,
I mean, CSC.
right.
I mean, it is a 6th order equation. If you phrase it like that.
Yeah, but I don't know that. I mean, that at least you can reduce to a 4th order equation. I don't know if that's possible in this case. Yeah.
I mean, so the cheaper way to think of one higher Chern form harmonic. And I would have imagined that this sort of formalism would be exactly, I mean, the PD corresponding to this form would be exactly that.
Okay. Well, I'll have to. You'll have to show me that.
Yeah, I mean, I agree with this. But okay, what is the Putaki invariant, for instance, that you get out of this form?
So it's written somewhere. So step 3, I integrated over the fibers, and I got. Oh, do you mean like the Donaldson-Pataki invariant or the? Yeah, so integrating this over P1 would give you the analog of the Donaldson-Pataki invariant. Exactly, yeah. Yes, well, not this formula, but you can do a similar fiber integral of equivariant forms to get the Hermite Einstein equation. You need a different setup though, because you need a vector bundle over the total space. Yeah. Yes.